So this is about coastal resilience. It's a little bit of an overlap with the previous talk on harbors because it's obviously affected by things like sea level rise. But in a very broad sense, coastal resilience, is the ability of coastal communities and coastal ecosystems to resist things like storms, flood events, sea level rise, heat events. So it's broader than just sea level rise. So why are we proposing to do this? Maryland and the Middle Atlantic states are the third highest rate of sea level rise in the nation. So I'm at the hinterlands of the Eastern Shore. Every day we are losing acreage, we're losing marsh. Our islands are being submerged and we're losing houses. Nuisance flooding, aqua alta, king tides, wherever you want to call it, is happening every day, so that even in Dorchester County, people at the Horn Point Lab where I work get calls saying the school buses are taking your kids home now because of extra high tides. So this isn't some theoretical issue that will happen in years to come. It's happening right now. And so that's the focus of this session. So we have some great speakers. First is Joe Fernando, and he's from Notre Dame. He has roots in Maryland. He told me before, he went to Johns Hopkins at the same time one of our Horn Point faculty members, Bill Boycourt, did. So I'm gonna let Joe be the first speaker, and you can either speak here or from your seat.
All right. So thank you very much. In fact, when I was asked to come, I was so pleased to come here. And first of all, I had to congratulate Peter Goodwin, being the new president of the Center for Environmental Studies. I knew Peter for a long time, and we had experiments side by side. He was doing, at Caltech, he was doing experiments on sediment transport. Next door, I was doing experiments on turbulent mixing at that time. But Peter understood things much better than I did, and that's the reason he's here today. So anyway, rather than talking about my own thoughts, I thought it would be a good time to give a little bit of an overview of what the coastal engineering community is thinking. Because 2 weeks ago, there was a workshop organized by the National Science Foundation on the challenges of coastal engineering and to chart the pathway of research for the next 10 to 50 years. So I thought I should give or encapsulate some of the thoughts that the community gave, what should be the best challenges which we should handle in the next 50 years or so. So the organizer, the chief organizer was one of my colleagues, Andrew Kennedy. So I asked him what the final outcomes of this one. So he said that, oh, it's not finalized, but he said these are some rudimentary thoughts from the workshop, which will go into a print version some point. So these are not official. The first one is the adaptation to sea level rise and other stressors. So as we know, sea level rise is a much often thought about and talked about topic. The sea level is rising since 1900s, about 20 centimeters on the average it has risen. And since 1993, it has risen 7 centimeters, so it's accelerating in some sense. So there is a real challenge because the coastal areas are at the brunt of the sea level rise. Some small islands are disappearing, so some are very worried that these things are coming about. So sea level rise can produce saltwater intrusions which affect the ecological systems in the coast. And they also basically have salinization of the groundwater. So that's a big topic to discuss in the future. So these are the topics that is hanging around and had to be understood. And unfortunately, this doesn't go across the globe. You know, I visit Sri Lanka because I'm originally from Sri Lanka. So I visit Sri Lanka often now because I have 2 big projects there. And one thing is that they are building up a port city, which is a 1 meter height. So like they never knew about the climate change. So here I make it forward here. Which one? The green one? Okay. Yeah. Now, here you can see the bottom left in Colombo, Sri Lanka. This was maybe about a month ago. So they are building up this city, which is 164 acres. We still talk in acres. Acre city funded by Chinese, and it has a lot of infrastructure, shops, government offices, and this is in the brunt of this, the sea level rise. So it hasn't been given much thought in some places, just on the economic grounds. So somehow this global communication of these kind of difficult issues has to be considered beyond the political realm, I think. Then going back will be this. All right, yes. And the other stressors. So that the other stressors are, some related to climate change, and some related to decadal oscillations, the natural changes over long time periods, like ocean acidification, the temperature rise of the ocean. When the temperature rises, we know that the plant communities flourish. Now in Australia, a lot of new plant communities coming up. In Alaska, you have new plant communities and as well as mangroves coming up. So that basically natural defenses. So you have different types of defenses coming up, although climate change is not very good overall. So that basically has to be thought about. And also the other stresses include intensification of cyclones or hurricanes here. That basically produce large storm surges, which actually affects the coastal areas directly. So there is a certain amount of resilience by the coast, but still those things are real problems, specter, which we face now. Then the next one, I don't want to go into very well details. I have only 5 minutes, I was told. So the coastal disaster resilience, which is the topic of this panel. Now, the resilience is offered by nature to a certain extent. That includes that you have mangroves, you have sand dunes, you have steep slopes, and so on. And the wetlands, partly. And that offers a certain amount of resilience, but not the full resilience. Now, for example, when we start tinkering with this, this is upper right-hand side. You can see this is in Japan. I have 2 more minutes. In the eastern part of Japan, and you can see that there was a steep gradient. And then they opened up this for access, economic reason, recreation. And you can see during the Tohoku, and then put a small seawall there just to prevent. And you can see during the Tohoku earthquake, the tsunami came right in through this. So you can see you tinker with the natural defenses. Natural defenses cannot offer everything, but you tinker with it. And that basically has some issues when we do that. And the wetlands, as discussed earlier, one of the speakers and also from the audience, that also has certain limited resilience. For example, the Corps of Engineers, that their rule of thumb is every mile storm surge travels, the height of the storm surge decreases by about a foot. But that's not enough for the full resilience. You have to have engineering solutions coming in without compromising the other type of natural resiliences. So there are many, many to discuss. Then you go back, the bio-initiated inspired designs is the old concept. That means you go hand in hand with the nature. So you get the wisdom from the nature and use what nature offers, those lessons in designs. A good example is these groins. When the groins were designed, they thought about that this is like a headland. You dissipate energy, you control a certain amount of sediment transport, then you develop technologies. So that's called biomimetic technologies, that you kind of imitate nature. And then risk-based designs, these are kind of new concepts, came from the ship design community. That means you look at the whole, I don't have time, the whole design, and then you identify various types of the problems you have, and every protocol, every regulatory restriction you obey for those types of designs. And there are a few other things, the evolution of Arctic, renewal of infrastructure, interconnectivity of the complex systems. All those are new issues that are on the horizon, and I hope we have a little bit of time to discuss them. Thank you. Sorry I took a little bit more time.
Our next speaker will be Dr. Hali Kilbourne, who's an associate research professor at the Chesapeake Biological Laboratory.
Okay, so I'm Hali Kilbourne, in case you couldn't hear since the mic wasn't working. And so I actually should start the slides.
They're going to cue it up.
Okay. I thought it would go hot. Okay. Okay, so I'm Hali Kilbourne. I was told to say a few words on coastal resilience. So I took some time to say, what is coastal resilience to me as an earth scientist, an oceanographer, a paleoclimatologist? And so I came up with a short definition, really: maintaining sustainable human and natural systems in a changing world and in the face of extreme events. So sort of combining this sort of slow change in the statistics of extreme events, in sea level rise, with the more traditional coastal resilience ideas of just extreme events. So weather events or tsunamis, et cetera. So that really sort of summed it up for me, and I thought I would sort of expand on some of the challenges that I see in studying this. So with the idea of trying to open up discussion about what are the challenges. So this is just a few ideas. So my work tends to be on the physical climate side and physics side with geology as well. And so that's where I start out with, is really projecting what the future has in store for us, whether it be changing frequency, intensity, or tracks of tropical storms, or long-term changes in sea level rise, but even things like the changing patterns of precipitation and temperature. So things like the drying out west causing more susceptibility to fire, or changes in the intensity of just afternoon thunderstorms. And I wanted to give an example of that. I've actually been working with Slava Lupšić a little bit on getting into trying to figure out what the changing storm statistics and extreme events that need to be engineered for. So I'm not in the engineering sector, but I can do the physical science to look at how we are going to, what we need to prepare for. What are those thresholds that we need to engineer for in order to reduce the risk of coastal systems? So then the next challenge I came up with is really sustainably managing coastal ecosystems to really preserve those ecosystem services. And that really encompasses a lot of what I see a lot of people at UMCES doing, whether it's for food and fisheries, recreation, just erosion control, excess nutrient abatement, or long-term sustainability issues of carbon storage. And then the third is not my bag necessarily, but is the engineering solutions of trying to plan infrastructure that can withstand these changing statistics of extreme events and our projected changes in the system while preserving those ecosystem services. So that's my perspective. Thank you.
Next we'll hear from Ming Li. Ming Li is a professor at the Horn Point Laboratory. He's a physical oceanographer that's working on stormwater inundation and flood prediction.
Already gave a great introduction to the topic. So I'm going to be talking more from look at the challenges from a modeling point of view. So to me, there are two major challenges in terms of dealing with coastal risk and resiliency. One is the prediction. When the storm comes in, And can we predict where the storm may make landfall? What kind of flooding will be generated? And then another topic challenge is that how do we respond to that? I'm going to, how do we manage our coastlines? So in terms of prediction, there are two kinds of prediction I can see. One is that short-term prediction. So we have a hurricane sort of developing in the tropical Atlantic, where it's going to make that landfall. So that for that kind of problem, I think that over the last few decades, we have made a lot of progress in terms of predicting hurricane tracks, and by doing ensemble techniques or by using final resolution global circulation models. So we're doing a pretty good job of predicting the storm track, predicting where the landfall might be. What we are lacking in progress is that we're not doing as good a job in terms of predicting the hurricane intensity. So particularly as the hurricane approaches the continental shelf, sometimes the storm can the intensity can decrease. It's like Hurricane Irene. People were embraced for a big storm surge, but end up, the storm get weaker. Sometimes we get the storm get more intensified, like Hurricane Sandy or Hurricane Harvey, and that actually the storm get more intensified, more intense as it approaches the shore landfall. So one of the things that's affecting this hurricane intensity prediction is that we need to better understand coastal mixing process that's affecting the sea surface temperature, which provide the fuel to the hurricanes. And once you get the hurricane wind right, I think that it's pretty straightforward to get the storm surge right. What's getting tricky is that once you want to take the storm surge prediction to get to the street level, inundation prediction. So, for example, if you want to predict, that's where the emergency managers might be interested in. So how do you, so we have made some progress in terms of, using digital elevation data over land and try to project the water levels over, storm surge over land. But we are sort of not doing, we still need more work trying to understand how when the storms comes in, waves come in, how interact with buildings, with infrastructure, how do we better parameterize how the vegetative surface, such as salt marsh, seagrasses, they could slow down the current storms. They could cause waves to dissipate. So those are sort of emerging science topics. Of course, we also want to be able to project onto the future. If a storm comes in 20 years, in 50 years, what will happen? As you know, that the weatherman can only predict make weather forecast by 2 weeks. So it is very difficult to, even with climate model, to predict, the extreme weather in the future. However, there's some, even from the precisely particular storm. But it can do the statistics of the storms. It's been found that storms are going to be more, there are going to be more extreme storms, maybe fewer extreme storms in the future. We know the sea level rise is going to be, there's going to be sea level rise rate is going to be accelerating, and the ocean temperature is going to be warmer. So we want to be able to, there's ways to try to consider how those warm ocean temperature, high sea rise, translate into higher storm surge in the future. Then in terms of response, how do we manage our coastline? Is that we're going to build high seawalls, levees, or we're going to use a more natural system like salt marsh, seagrasses, or living shorelines? So usually the prediction dictate how we respond, but sometimes how we respond can affect the prediction too. So how do I go to the next? Green. So since we're in Baltimore now, I have to show this to you. So the top panel shows the inundated area near the Baltimore Harbor during Hurricane Isabel in 2003. The blue line that's showing the flooded areas, the streets around here flooded. The other is a prediction. Take the prediction to the end of 21st century. At high emission scenarios, how much more area would be flooded. So the storm surge height was about 6 to 7 feet in 2003. Hurricane Isabel is going to be double that. So, and just last slide. So the other thing we did was to look at how the we manage coastline have effect on storm surge. If you look at the bottom panel here, is that if you let the low-lying area flood it, in fact, the storm surge height will be smaller than if you say, I'm going to protect everything, I'm going to erect walls at the covering coastline. The storm surge height will be almost like a meter higher. So one of the things that the strategies that for us to consider is that whether we actually help to people in the low-lying areas to migrate to higher land instead of try to build like seawalls. So I had so I was talking to my neighbor about saying, maybe we can essentially get flooded to save Baltimore, Washington, D.C. He didn't talk to me anymore. Yeah, that's my.
When you use the microphone, just hold it right up to your. Our next speaker is Allison Reilly from the University of Maryland College Park, where she studies coastal risk and resilience.
Thank you. Yeah, so I'm Allison Reilly. I'm an assistant professor at the University of Maryland in civil engineering. So I thought I would talk today about not only coastal resilience, but also the challenges and some opportunities in this area, all from my perspective, right? So first, I think I need to give a little bit about my background in order for some of this to make sense. So my degrees are all in civil engineering and environmental systems, or infrastructure systems, but most of my training is in risk assessment. So my postdoc is in risk assessment, and I spent time at a research and development center with DHS doing threat and risk assessments. So what I do now is understand how people make decisions under uncertainty about infrastructure. Right? So that could be, why do people mitigate their homes? Why do people leave? What is it about the infrastructure services that are being provided to them that induce them to make certain decisions? So the thing I've learned about risk and risk assessments is that it transcends disciplinary boundaries. And this really frames my perspective. It's not an engineering problem, it's not an ecology problem, it's all of the above. So one of the first challenges that I see, especially with coastal resilience, is how do we overcome and really start to integrate knowledge? So the coastal problems and the solutions, from my perspective, really exist at this intersection of many fields, from economics, hydrology, engineering, sociology, anthropology. One of the problems is that we have vocabulary. Our vocabulary tends to be very disciplinary specific, and our traditions and methods are also very, very siloed. And training to become an interdisciplinarian takes a lot of time. The true interdisciplinarians that I've met, that I've been so fortunate to meet over my life, have been working at these problems for decades and decades. They've also left academics for long periods of time, worked at nonprofits and worked in government, to gain this experience and to actually contextualize what it is that the knowledge they've created and the theory they've created, and to deepen their understanding. So I think that this creates a lot of opportunity for us. So I think we already have existing frameworks for how to create interdisciplinary programs for our students. The environmental sciences program is a great start. We need to expand that. We need to bring engineers into it, social scientists. And we also have to look at what type of institutional barriers exist right now in training our students. So example, at the University of Maryland, there's tuition differential if I want to send students to a different department, which makes it more difficult for some students to get training outside their field. The way we do bean counting of advisors, so it makes it more difficult to have co-advising. But there are ways that we can overcome this, send our students to intern in other people's labs, create more service-based learning projects on coastal resilience that you can create large programs to get students into these programs, create diverse groups of students. And I think the benefits from this type of approach could be really real. If we look at engineering, where the growth of women and underrepresented minorities have been, it has been the area of interdisciplinary fields, including my own. So if you look at my field, women are highly overrepresented. We have to actually think about recruiting men into our field because we are overrepresented, women are. So this isn't surprising. In engineering especially, women and underrepresented minorities have been marginalized from traditional disciplines for a very long period of time, and they've basically forged their own path. And coastal resilience is one of them. One other specific challenge that I'd be remiss if I didn't speak to right now, that I'll be able to keep it brief, on coastal resilience is the concept of inclusive adaptation. So a recent study has come out that where we look at where most of the money goes for infrastructure or coastal protection and adaptation goes to wealthy communities. This is not surprising. When we look at exposure, it's mostly value-based, meaning dollars and cents here. What is insured and what is insurable? Also, when we look at hazard mitigation block grants, which, by the way, will increase orders of magnitude starting in 2019, in that 6 to 8% of all federal disaster grants have to go to mitigation. Where we look at where this money often goes, it goes to communities that have the capacity to apply for these grants. So we need to make sure that communities like on the Eastern Shore are able to access these grants. So one of the ways I'd say to continue to address this problem is we have to continue to create and treat coastal resilience as a social justice problem, especially with our students. So for example, in engineering, civil engineering is a social justice problem. Access to infrastructure and its services enables productive and healthy communities and citizens. So anyways, I'm gonna stop there. I really thank you for this opportunity to share my perspective, and I look forward to the discussion.
Our next speaker is Emily Russ, who's a graduate student within the MEES program, and she's at Horn Point, where all of our students are above average.
Thank you, Mike. Thank you for the invitation to serve on this panel. I'm very excited to be here. And so I just wanted to start by saying that coastal resilience has been an interest of mine since before I knew it was an educational or a career path. And it all stems from this interest in hurricanes. And I actually experienced my first hurricane when I was 2 weeks old. It was Hurricane Hugo, so I feel like a very strong connection to these types of events. But beyond that, I grew up in North Carolina. It's a state that gets impacted by hurricanes a lot, and I've seen a lot of coastal change throughout my life. And so that was where I wanted to go with my education. And so I ended up getting a bachelor's degree from NC State, where I studied marine and coastal resources, and then I continued on into a master's program there in coastal geomorphology, where I studied the impact of storm events on the Outer Banks, specifically how the shoreline has moved throughout history there. Well, not history, but modern history. And so it was really when I came to UMCES that I started to see this whole idea of coastal resilience and how it's a very interdisciplinary field. And so when I first came to Horn Point, my project was, we were forming ideas of it, but I got involved into this project dealing with the Conowingo Dam and the infilling of it and how that affects the total maximum daily loads that have been set by the Environmental Protection Agency. And so I was learning all about the science behind all these water quality issues, but what I also was introduced to was the politics around it and how it's a very political issue. It's got a lot of different social aspects coming from it because there's a lot of people trying to figure out what do we need to do, who do we blame, how do we fix this? And so I actually was able to obtain a Coastal Resiliency Fellowship from Maryland Sea Grant, and as part of that, I have forged a relationship with an outreach mentor that works with me. She's a Maryland Sea Grant extension agent, and so she does a lot of local on-the-ground work in promoting this type of resiliency. And so I've gotten to learn a lot about these types of stakeholders, and I've been able to get involved in the communities and try to understand what they need from how they want to make their coast more resilient, what they want for their communities. And so I'm also honored to be one of 4 UMCES graduate, well, soon to be graduates, probably students, that are going to be starting a Canals Fellowship in February. And I'm actually going to be working with the U.S. Army Corps of Engineers. And one of the big issues that they're working on is coastal resilience. And it's coming full circle And I'm excited to be working on projects related to hurricane resiliency, especially in terms of really recent hurricane events that we've seen over the past couple of years. And I'm excited about the opportunity to work with other federal agencies and reaching different types of stakeholders than I've reached. Instead of working in the communities, I get to work up and I get to work with the federal government. I get to help plan workshops that are going to be on resiliency planning committees. So I'm just really honored to be able to do that, and I'm excited about it. And so I'll be happy to take any questions as part of the panel, but I'll leave it up to you.
Well, those were great presentations. We'd like to open the floor for questions, discussion. This is Blake Clark, who's also an above-average graduate student at Horn Point.
Cool. Thank you, guys. This could really be for anybody, but I'm curious what time frame sort of the focus of research into coastal resiliency should go into. Like, we already see the effects of climate change, and depending on the projections, it could be really bad in 2050. So should we focus on the 2020, 2030, or the 2050 range in terms of our adaptation?
Let me test it. Okay. So I'll answer that as the paleoclimatologist in the room. So I personally, I think the answer to that question is just depends on what you're talking about. If you're building a road and you expect it to last 100 years in the coastal zone, well, you'd better be thinking about what sea level is going to be like in 100 years. If you're building a beach shack, same thing. Do you expect it to be around for 30 years or not? So I think the answer to that question is really, it depends on what you expect the timeline of your built environment to be.
Yeah, just I think on the flip side of that is that there are so many communities right now who are being affected, and bringing insight and awareness to what is going on at present is critically important. And we have to bring into the planning, and we have to think about long-term planning as well, but also right now. What do we do right now?
So I want to make, come on, okay. Make a comment on that. Now there is this ongoing concept which you call adaptive management. So when you design some infrastructure, you basically design for 10 years or whatever affordable limit, but you keep options open that as you learn and develop these things, then you can make changes. So this is always going on now, especially with Corps of Engineers, that adaptive management. So you design for 5 years or 10 years, and then if it happens again, then you keep on evaluating how the things are going, and then the design is open for modification. So that saves huge amount of funding going for these projects.
Can I add to that? I think that you're asking a very good question. If people say it is 100-year flood, why do I care, right? So I think that the answer to that is either 15 years, 30 years, because they tie into your mortgage loans. I think that you have to have some, try to tie it into some economic, cost-benefit analysis so that people really could, say, if I'm going to buy a house in Norfolk, say, I'm going to live there for 15 years, that maybe I have to worry about whether I can get out of the house during high tides. That's going to impact you. So I think that we need to look at, of course, the short terms, the sea level rise rate is going to be effect will be smaller. As you go to end of century, there's going to be much higher, sea level. Then also uncertainty will be higher too. So I think we need to do both different time horizons.
Actually, one thing I'd like to add to that is that when we're doing a lot of the planning now, and especially when we're looking at do we build seawalls, we have to also think about long term, about how humans will respond to these interventions. And what we often see is, for example, if we build seawalls, more people start to develop behind these seawalls. And if you look at like Japan over a 1,000-year period, where do you see the most death and destruction? Behind larger seawalls. They have great records, we can look at that. So we also have to think about how people will adapt and respond to these interventions, and without thinking about that behavioral response, I just don't, I don't know if we're going to be as productive as we think we're going to be.
So I think Don Bosch and Peter Goodwin are good people to comment on that, because I met Don first at the Louisiana Coastal Area Science Board. He was the chairman, and he stepped down, and Peter took over. And there we had a lot of seawalls, and the storm surge barriers were building up. And the response from the people who are constructing that, we don't have time to think many things, what the people think, but we just want to save people. Next year, when the storm surge comes, we want to protect you. So, I mean, my question was, why was the environmental assessment was not done? Because they just don't have time. It's just responding as things come. So there is a balance between these two issues, and I don't know how to comment, but probably they might make some comments. They have a better idea on this.
Question? It works.
Okay, yes, I'm Jaap Dijken from the Netherlands. Sorry. I'm from Deltaris Research Institute, and we do a lot of work on coastal defenses and also nature-based solutions. But my problem with the nature-based engineering is that I believe that the level of maturity compared to our classical engineering is about 19th century. So we have to do a lot of research still. And my problem is that the civil engineers, the classical civil engineers, it took them 200 years of trial and error to arrive at the level they are now. We don't have 200 years to learn the trick. Now, I would say that is the big challenge for the coastal engineers. Who wants to answer that? To say something clever about that?
I don't think that it's only nature-based engineering. I mean, it's not, we know how to avoid risk. We know how to elevate homes. We know how to not develop. It's not politically palatable, but we know that, I mean, it's not just one thing. We have to look at, and from my perspective, a suite of solutions and interventions, and nature-based solutions is, of course, one of them. And you're right, it's in its infancy, and it will continue, our knowledge for it will continue to expand. I think we're starting to get a lot of knowledge out of the state of Maryland of nature-based solutions.
I would also point out that nature-based solutions have had 500 million years to develop. And so, as an example, I work in the tropics. I've worked on a low island called Anegada in the Virgin Islands, and its highest point is a tiny little knoll that's 40 feet high. I watched a buoy offshore of that island when Hurricane Irma hit, and those waves, significant wave heights of 40 feet. And I knew people on that island, and I was freaked out. But you know what? The reefs helped, the dunes helped, and people on that island survived. So to me, that is the absolute power of the natural engineering. I was shocked.
One last question, Dave says. So I'll make a comment, not a question. Coastal resilience is something that we really should harness the power of the entire university system of Maryland. You heard that it involves economics, anthropology, engineering, sociology, many fields. We have some great faculty and students at UMCES, but obviously we can't cover all the aspects. And so hopefully this afternoon, and conversations will continue with our various USM partners to see how we could face this big challenge together. Thanks.